So guys, today we are going to discuss about time dependent Schrödinger's equation. Okay, so for this we have to consider a particle which having mass m and moving along positive x direction. Okay, then the potential energy then the potential energy of the particle is Vx, and also the momentum is Px, and the total energy is E. For better understanding, we take this three-dimensional. This is positive x direction, this is positive y, this is positive z. Suppose consider a particle is here in moving in along the positive x direction, which having mass m, momentum p of x, and potential energy v. Okay, v of x. Now the matter wave associated with the particle can be represented by one-dimensional wave function h. The matter wave, this is a particle which is having mass m, momentum px, potential energy vx, and the matter wave is associated with this particle, and we can represent this is the wave function in one-dimensional h. Psi equals to a into e to the power minus I into e into t minus p of a into x divided by h cross. Or we can write this as psi equals to a into e into I to the power I into p of x into x minus pt divided by h cross. Okay, so give it equation 1. Now partially we have to be differentiate equation 1 with respect to t, then we get the result. So we have to write down this first. Psi equals to a into e into the power I into px of x minus at divided by h cross. Okay, so if we will partially differentiate with respect to x, then we can write dou psi by dou t equals to, so here a also be nothing, a also 0, then we can only write this minus of I into e by h. Then again the similar part, a into e to power I px of x minus 80 divided by h cross. Okay, so we can write this as minus I by h cross minus IE by h cross into psi, which is same to the equation 1. Psi equals to, this is the same value, so we can write this as psi. So after we can write this also, e into psi equals to I h cross dou psi by dou t. So we can name this equation 2. Okay, so we can write this equation 2. Now similarly Similarly, we can partially differentiate equation 1 with respect to x. Then we get the result h. So the equation 1 is psi equals to a dot e to the power I into px of x minus at divided by h cross. Okay, so we can partially differentiate this equation 1 with respect to h. Then we get dou psi by dou x equals to I px by h cross a into e, again I px of x minus at divided by h cross. So here we can write it I px by h. We can substitute the value of psi here because this is the same value equation answer. We can write psi, we can solve it, px into x into psi equals to minus of I h cross dou psi by dou x. So this is the equation 3. Okay, so according to classical mechanics, total energy of a particle, then we can write it E equals to px square divided by 2m plus v. So here px equals to momentum and the 2m equals to kinetic energy. Okay, so we can write it this. We can multiply, we have to multiply psi on both sides, then you get p psi equals to px square by 2m plus v into psi. Substitute the value. Now we have to substitute the value of p and px. Then we get IH cross dou psi by dou t into equals to 1 by 2m minus IH cross dou psi by dou x square plus v psi. Okay, so we can write it also IH cross dou psi by dou t equals to 1 by 2m minus of h cross square dou square psi by dou x square plus v psi. Okay, so this is the time dependent Schördingers equation, wave equation in one dimensional dimension. Okay, so we can write here in 3 dimension. So in 3-dimensional form we can write it h minus of h cross divided by 2m del square psi plus v psi equals to IH cross into dou psi by dou t.